Hey, geometry friends, here we are working in chapter 5, and we're looking at section 5.2. We're going to talk about medians and altitudes of triangles. So, our vocabulary includes those words, median and altitude. Let's see if I can get my screen to work. So, a median of a triangle refers to, and this is going to be a little bit confusing, sort of, kind of. But a median refers to a segment that the median of a triangle has three medians. It refers to a segment that goes from one vertex to the midpoint of the opposite side. So that this isn't necessarily an angle bisector. This isn't obviously it doesn't look like a perpendicular bisector, but it does bisect the segment on the other side. And a triangle has three medians, as you would expect. If it has three sides and three vertices, it'll have three medians, right? And just like when we were talking about in the last section, the angle, the perpendicular bisector of the triangle side and the angle bisector, medians also meet in a point. All right, so we know what the medians are. It's a segment that goes from one vertex to the midpoint of the opposite side of a triangle, and a triangle has three medians. The centroid is the point of concurrency of the medians. So the centroid would be all of these points together, all of these segments where these segments actually intersect. That's our centroid. So next we'll use this triangle to discuss the altitude. So now a triangle has three altitudes, just like it has three medians. It has three altitudes, and as you may suspect from the word altitude, an altitude really just means the height of a triangle, right? So if I'm talking about the height of a triangle, I have to consider the orientation of the triangle. So if I'm thinking about the height of a triangle, ABC, and I'm going to talk about the altitude from A to CB, I need to orient it like this so that I'm in my mind. Even you might not be able to do this like on paper, but you need to think about the altitude as dropping a perpendicular from one point straight down to the side, the other side, right? Sometimes it can't be done in exactly that way, but this is an altitude. So an altitude is a perpendicular line that goes from one point of a triangle or one vertex of a triangle to the opposite side. And I'm going to rotate and draw all of the altitudes here. So the altitude from C to AB will be this guy over here, straight down and 90-degree angle. I know this is a little bent, but you guys get where we're going. And let's see if I can do it without ruining everything. We're going to rotate one more time. I think I'm going to mess up this picture. Don't worry. Just pay attention to the green one right now. When I do the altitude from B to AC, I need to keep it kind of like that, flat. And then I'm going to talk about the altitude there where I drop a perpendicular straight down. This doesn't look great, but what I want to show is that a triangle has three altitudes, and the intersection of those points, so that's what an altitude is, the intersection of those points, the concurrent point is going to be the orthocenter. So the orthocenter is the where all of the altitudes meet. I want to just point out one thing because I think this is necessary to point out. Sometimes the altitude of a triangle, the altitudes of a triangle will not actually meet where you want them to meet. So if I had a triangle like this, right, and this can be our ABC again, the altitude from B to AC will not actually hit AC because you see, if I draw a perpendicular line to, and the way we would really say it is to the line that contains side AC. So I'm thinking about this line that I have in gray highlight that contains AC. I can draw my perpendicular, my altitude. I can draw my altitude from B straight down there. So what this shows me is that all altitudes are not within the triangle. They're not always going to be inside. and therefore all orthocenters will not be within the triangle. Does that kind of make sense? Because I guess we could rotate this around. I didn't try it, but let's see what happens. If I rotate this guy around and did the altitude from A, the altitude from A would be, remember we have to kind of make this parallel, and I'm thinking about, I don't know why that happened, I'm thinking about kind of extending this line CB. The altitude from A would end up being out all the way out here, right? Then the altitude from C will go this way, but if we extended it in directions like this and extended this guy, the orthocenter is actually out here. Isn't that weird? All right, so just keep in mind when we talk about the height of a triangle from a particular point, that line may not necessarily be drawn, or the altitude may not necessarily be drawn inside of the triangle. So here's the centroid theorem. It says that the medians of a triangle intersect at a point called the centroid, right? So that's just giving us the name. And then that is 2/3 the distance from each vertex to the midpoint of the opposite side. So the relationship here is that P is going to be 2/3 the distance from this side to this side. So what does this mean? Let's look at what we're given. AP is 2/3 AK. BP is 2/3 BL. CJ is 2/3 the whole thing. So it kind of splits it into, like, I don't know, thirds in a way. Like this is 2/3, this is a third. I don't know if that makes sense. This is a third of this segment. This is 2/3 of this segment. So AP is 2/3 where PK is 1/3. JP is a third where this guy is 2/3. So it has that nice relationship there. So let's see if we can figure out some information. So here, we're going to use the centroid theorem. We're told that triangle ABCQ is the centroid. So we know some information. We know that these are all split in half. These are all medians. And BE is 9. So we know that this is 9. We need to figure out what BQ is and QE is. And you can see BQ is going to be 2/3 of BE. Since BE is 9, 2/3 of BE is 6. And so that's BQ. We can look at it as 1/3, QE being 1/3, or we can simply say BQ plus QE is equal to BE, right? I don't know where that came from. Is equal to BE. And therefore, since BE is 9 and BQ is 6, then we can get that QE has to be 3. And so that's one way to get through this. So that relationship, 2/3 to a third, or 2/3 of the whole thing, is what we have when we deal with the centroid. Okay, so in triangle JKL, PT is equal to 2. Okay, so we have a 2 here, and we are asked to find what KP is. Well, you remember we know that from the image that this is the centroid. The centroid cuts the intersection point. The centroid cuts each segment of the median into, in a weird way, thirds. So this is going to be 1/3 of the whole segment, and this is 2/3 of the whole segment. And so if this is 1/3, if 1/3 is 2, 2/3 will be 4. So KP is equal to 4. Yeah, that's really it. Okay, so here is our real world example. Now, a performance artist plans to balance triangular pieces of metal during her act. When one such triangle is placed on the coordinate plane, here's where its vertices lie, right? What are the coordinates of the point where the artist, should support the triangle so that it will balance? So we're going to find the centroid, right? That's what we'll do. So after drawing a picture of what this looks like, we know we're going to have to find the centroid. And the centroid is going to be, remember, you're going to find the midpoints of each side, and then you're going to figure out what the line is. This is going to like really call on some old, that didn't work out. We're going to find out what the line comes out to, and they're all going to meet in one point. That's going to happen. That is fact. I know it doesn't look like it, but that's what we're going to do. So we have to figure out a couple things. One thing, okay, so I got really knee deep in this, and I was like realizing that we're just going to go over. So I'm going to stop here, and we're going to pick example 3 up in another video. So we're going to stop here, and we'll just pick it up. It's all good. All right, so let's leave this alone, and we'll pick up example 3 and 4, and then we'll be done 5-2.